Now, we said again, good afternoon. Today we will go over the last theory class. We have some leftover things about GMM, but since this class here is shared among both the computer science and quantum computing course, and the other course doesn't, the quantum computing doesn't have the GMM in their program, I will finish. We say we will have 10 more minutes about GMM. I will take some minutes from the lab to discuss what's left from the GMM. I will skip the proof that the GMM converges because we don't have time to do that, but we'll spend a few minutes to understand how to use it, and in any case, that's related to how we will use it in the laboratory. So I will not go through the GMM now. I will just move to the next set of slides, and then for those who are from computer science, we will say a few words about GMM later during the lab. So the last topic we need to address that we left for later during the whole course is how to address the issue where my model gives uncalibrated scores, and we'll see as a side effect we will also find an effective way to combine the outputs of multiple classifiers. What does it mean? It means that you have trained several models during this course. You have trained Gaussian models, you have trained logistic regression, linear, quadratic, you have trained SVM, and hopefully from today you will also train GMMs, and you're seeing that these models have different information, give different performance. Now, depending on the kind of models, it may turn out that different classifiers are able to extract different information from the data. So they may disagree in their label assignments for some samples, and when there is disagreement, there may be benefits in combining multiple classifiers. For example, a simple way, imagine that you have to classify at that sample xt, you have classifier 1, classifier 2, classifier 3. This says the label is 1, this says the label is 1, this says the label is 0. I can combine the 3, and maybe label 1 will be the correct one. So I may try to combine several classifiers. Now, simply choosing the label that is output the most is not the most effective way, the best way of doing it. We will see how to do it, and we'll see that it's a way that is similar to the way we will address score calibration. Okay, other questions before we start about previous works and previous laboratories, especially on this part? We have already discussed about score calibration, so other questions about what we said on this topic yet until now? Okay, then let's go back to what we did and let's analyze what happens for our models. We have said that if everything goes well, we have a classifier that gives class posteriors, these class posteriors, or likelihood ratios if we prefer. If we have a generative classifier, likelihood ratio. If we have a discriminatory classifier, this will be class posteriors, but we have seen how to map them to something that resembles log likelihood ratios by compensating the training set priors. And we said these are well calibrated when we can make effective decisions with these scores. What does it mean? It means that typically we have said that our assignments are made by comparing a score with a threshold, which means that for our decisions to be effective, the threshold must be good. So when we have a classifier, we have two things to take into account. We want a classifier that is able to obtain good performance, so is able to separate our classes, but we also want to be able to find a good threshold for the specific application. For example, we may have a classifier that is very bad at separating our samples So the classifier is intrinsically a large error because the classification rule is bad. So the scores it gives are inaccurate. They are not representing correctly. They are not useful to estimate the class of the samples. However, we have also seen that what may happen is that for a given application, we may have a classifier that gives good scores, but for some reason, these scores are not well calibrated. So the threshold that we use is not the best we can use for that specific application. Now, the former problem can be addressed by changing the recognizer. So for the former problem, we need to find a better classifier. For the latter problem, we have said we have a good classifier, but the problem is that we need to define a rule to obtain good decisions from the scores generated by the classifier. Now, well-calibrated scores are scores for which we know how to select good decisions, and we said typically this is a threshold that depends on the application prior and costs. If the scores are well-calibrated, they represent well-calibrated probabilities. So they allow to obtain well-calibrated probabilities. We can take cost-effective decisions that account for prior probabilities for the cost of different error rates in a way that we have seen is providing a cost that is close to the lowest that we can obtain with those scores. We have seen this when we were showing that well-calibrated when you analyze some models, you saw that there are models that are well-calibrated. For those models, we can obtain actual costs that are close to the minimum cost. The minimum cost is the cost that I obtain by selecting for every application the best possible threshold for that application. The problem is that there are models where this does not happen, and we have seen several reasons. For example, we may have models where the score itself has no probabilistic interpretation. In the SVM, we said that the score represents essentially a distance of a point from the hyperplane. It's not exactly a distance, but it's related to the distance of the point. But we can't associate to this distance a probability value. So there is no probability associated to the score S. Then we have seen models that try to provide probabilistic values, so probabilities of classes, but even in this case, even if they are optimized on a training set by reasonable criteria like maximum likelihood, we may still present, which typically provide, if we have enough samples, scores that are well calibrated. Even in this case, we may have either overfitting, which leads, we have seen, to models that are overconfident. The prior probability for one class when we have overfitting tends to become much larger than it should be. Or, to avoid overfitting, we may add regularization, but if we regularize too much, then our models may become underconfident. They will maybe generalize better in terms of hyperplanes, but the threshold that we obtain, the probabilities estimates do not behave well in terms of calibration. We have probability estimates that do not represent well the samples that we are going to classify. Even though we can modify them, we can change the threshold, so we can modify them to obtain better results, but the problem is we haven't seen how. So also, when we have generative models describes the distribution of samples. If the distribution of samples is a good model for the evaluation population, then what we get is a good log likelihood ratio that will be well calibrated. Otherwise, if there is distribution mismatch between the training data and the data that we test our model on, the density estimates that we use are not a good description of the evaluation data, so that may lead to what? Well, on one hand, bad model in the sense that the model itself may not be able to discriminate well the classes, large, min, DCF. But there may be cases where the model itself, let's say by chance, is still good at discriminating the classes, but this mismatch will still provide miscalibration errors. You have seen, for example, that the Gaussian model for the project data is able to well discriminate the samples of two classes arranged in this way, but this is an example of a model that is not, generative model that is not well suited for this data. The generative model that we find will provide high density regions in this area where there are no samples, and where there are samples, actually our model will not be well matching the distribution of the scores. Now, this may also lead to similar distribution mismatch may lead to calibration issues. So even generative models are not guaranteed to provide us results that are scores that are well calibrated. We'll see another example later when we discuss GMM. When scores are not well calibrated, it means that the decisions we make are worse than what we could make if we were using a different threshold. Well, now I was talking about thresholds, so I was implicitly talking about binary problems. What we say can be extended also for multiclass, but we will not see how to recalibrate the multiclass because we don't have the time and it will take more time than for the binary. So what I said, what is in these slides is true regardless of whether we are talking about binary or not. Of course, if we talk about LLRs, it's binary, but the same issues, well, except for SVM, apply also for multiclass problem. In that case, it's more difficult to define what we mean by miscalibration errors, but we will say a couple of words on that. And we will not extend. But what I said, of course, was for binary. In the case of binary, we compare score with a threshold, so miscalibration typically can be seen as we are using the wrong threshold for the evaluation population that we are classifying. Notice that we may even have a good calibration on the training set itself. So if we apply our model to the training set itself, it may have good calibration, but the model may provide scores that are not well calibrated for the application. So the goodness of the calibration depends on the task that I'm using my model on, as usual. The performance of a model depends on the site that I'm classifying as well. So we can't say that a model provides miscalibrated scores in absolute. It will provide miscalibrated scores for a specific classification task. If I change the classification task, then maybe distribution mismatch changes, so also the miscalibration level changes, and so on. So it's always referred to a task. So how can we reduce miscalibration? If miscalibration is related in the combination of using a recognizer to classify some data, then what we can try to do is to find an optimal threshold for the data. We consider a binary problem. A binary problem, we solve the problem of classifying a sample by taking the sample, computing its score, and then comparing it with the threshold. Then, which threshold should we use? Well, one possible answer is if the theoretical one that depends on the application is not good because our scores are not well calibrated, what we can do is try to find a different threshold that works well. How can we find a different threshold that works well without looking at the previous slide? So we have training set. Then we have, for example, validation set that you use for the moment to train the results, and then we have application data that we need to classify. How can we find a good threshold for this data here? You have, even without looking at the slides, you actually have everything required to solve this problem, and actually you already have the code to solve this problem implemented if you did all the laboratories. So with what? Yes? So how? So a possible way, like your colleagues said, any other option, any other idea? So who would do like your colleagues suggested? Nobody. So how would you do if you wouldn't do like that? So some suggestions. Or if you don't have any suggestions, tell me that you agree with your colleague. If you agree with your colleague, of course, you don't have any other additional suggestion. So who does agree? 2, 3, 4, 5. Okay, so we can do as your colleague suggested. We have a validation set, then we will ask ourselves whether this is a good validation set to use. But we have a validation set. On the validation set, we were computing min DCF. Min DCF was the DCF obtained with the optimal threshold for the validation set itself. So when we were computing min DCF for an application, we were trying all thresholds, selecting the one that was giving the best performance on the validation set, and then that was the threshold that we would use to compute min DCF. So what are we doing? Essentially, we're treating the threshold as a hyperparameter that we estimate on the validation set. If this is optimal on the validation set and the application data is similar to our validation data, then I can imagine that using this threshold that was optimal for the validation data will also be close to a threshold that is optimal for the application data. So my miscalibration for that specific application will reduce. Do you agree? So we treat it exactly like any other hyperparameter. We have an application in mind, we train the whole model making all the choices, including selecting the threshold at which we will score. So now we have, for example, we may have the PCA dimensionality M, the RBF kernel gamma values, the SVM value C, and now we have the threshold T. We have these 4 hyperparameters to tune. We tune them on some validation set, then we will ask ourselves whether it's good to tune this as well on the same data. But we tune all this. This will give the best absolute performance on the validation set and will give us values that we may hope will work well on application data. Now, 2 problems. One, as I said, this validation data is already used to estimate parameters of the model, hyperparameters. So maybe using exactly this data may lead to thresholds that are a bit overconfident. This does not represent really data that was unseen. But for now, let's leave this aside. We'll come back to this problem later. Second problem, what if I change the application? What should I do every time I change the application? What should I do? We should find again the optimal threshold. This is a threshold that was obtained optimizing the min DCF for the specific application pi t. If we now change the application, we need to redo everything. So we need to have our validation set at least, typically just the validation set because we are not retraining the models. We may want to keep this fixed. So the validation set is enough, but still we need the validation set and estimate everything from scratch. And what does it mean? How can we do if we don't know the threshold when we sell our model to different users, it means that when we set the model, we must also provide with the model the validation data and the tools to retrain the threshold for the user-specific application, which is possible, it's doable. This is one possibility, but it has some issues. If this validation set, well, there are some issues on the fact that, first of all, typically you don't want to distribute data with your application. So typically you don't want to put the validation data. The validation data itself may contain information that you can't distribute freely. And in any case, it increases the size of the model and the amount of processing that I have to do to adapt the model, which is not by much, but still, it's an inconvenience. Not only that, this may work well in some contexts, but if our scores are wildly miscalibrated, that means what? That, or not wildly, but our application, well, if we change, we need to know exactly the application. We can't do something like we said for the logistic regression, train for an application that is similar to the target one, and then if it's similar enough, things will work. Why? Because if we adopt this strategy, then this works if the application has this prior here. If we slightly change the prior even a bit, we need essentially to retrain the threshold because we don't know how much the threshold would move even when we have two applications that are similar. So if we have two applications that are similar, we can't know by how much the optimal threshold would move. It may move a lot. So if we don't retrain and we just rely on the fact that we have two similar applications, we may end up with results that are still that, well, if we optimize for one, the results may still be very badly calibrated for an application that is similar. Why? Because that depends on the dynamic of the thresholds. For example, okay, I will not give an example because it's complex, but in any case, we need to know exactly the application, and even if, as we said, if we change application, it's clear we need to retrain the threshold without proving that holds true even if we have application that looks similar. Even if we have application that looks similar, we may have the necessity of retraining the new threshold when we change our application even by few. So the idea here is, okay, we can do that. If we know the application in advance, it's doable. But can we do something better? Can we find a way that allows us to produce well-calibrated scores directly? If we have well-calibrated scores, then we don't have the problem. We know how to compute the threshold. For scores that are well-calibrated, the threshold is the usual, even in terms of effective prior, this. If you want to put the costs, you just need to plug them there. But if you work with effective prior, you don't need to put the costs. Then this holds for any application. And if we have close-by applications, we know about how much this threshold will move. So if a model works well, except for the fact that if it's well calibrated, even if we change the application, we just need to change according to the threshold and the model will perform well for the new application. So for example, you have seen models where the mean DCF, where you were looking at bias plots, the mean DCF was looking something like this, and the actual DCF was very close, which means that for any application in the range we considered, for any of these applications, using the theoretical threshold was providing the same results as using the optimal threshold for that application. This is an example of scores that are well calibrated for many different applications. So if we have a model that is providing scores that are not well calibrated, so for example, the mean and DCF look something like this. Can we obtain, can we make something out of these scores to make them calibrated? So can we transform the scores to make them calibrated? The answer is we can try to find a mapping between the scores and something that is a new score but is well calibrated. What does it mean? Well, essentially we take the scores of our classifier and we do some post-processing of these scores, so we manipulate these scores to produce a new score that is well calibrated. Now, there are different ways of doing it. The first thing that we ask is that our function f preserves the information of the scores. That is, the information of the score, we have always said that for binary problem, the minimum thing that we require for a score is that if a score is large, it favors class true. If a score is null, it favors class false. And that means that if we have two scores, the first is larger than the second, then the first is more in favor of the true class than the second. So regardless of how we map the score to probability, there is a higher probability that the first sample is from class true than the second sample. So the ordering of the scores should be preserved. If we have that a sample is more likely to be from class true than the second one, also after we calibrate the scores, we want this property to be preserved. We want the relative strength of the scores to be preserved, which means that our function, it's not written here, should be monotonic. So our transformation function should be monotonic and should map our scores to scores that represents a log likelihood ratio for the evaluation population. So they behave like a log likelihood ratio for the evaluation, for the application population. Now there are different ways that meet this constraint and allow us to obtain scores that are well calibrated. The first one essentially is a way to map scores to class posterior probabilities in a way that these class posterior probabilities are well calibrated. Remember that if I have class posterior probability, if I have scores that are well calibrated for a given application, I can map them to class posterior probabilities. So the being well calibrated is a property that I can transfer from the score to the class posterior probability. And I can do the same backwards. If I have a model that produces well calibrated posterior probabilities, then from this I can construct well calibrated log likelihood ratio that adapt to different models, to different applications. Essentially, the isotronic regression is a transformation that we will not see how it works, but takes as input the score of your classifier, and for the different scores gives you as output the corresponding class posterior probability for class 1 that should be associated to that score. So you will train it on a validation set that contains different scores, and from these different scores it will compute what is the corresponding class posterior probability that should be associated to that score for the validation set prior. Now this is again trained for a single application, but once we compensate for the prior, for the empirical prior of the validation set, as we have seen in logistic regression, what we get are models that provide well-calibrated scores. Essentially, this is done by training, and we will not see what, a monotonic piecewise increasing function that will look something like this, that maps all the scores to a class posterior probability. So here goes between 0 and 1, and all the scores are mapped to posterior class probabilities by estimating what is the posterior class probability of that class given the corresponding score. We will not see how to do it because in practice we will not be using this model, but this is just to cite that this model, if you look online, is one possible application, one possible method to map scores to well-calibrated scores. So as I said, this is one possibility, but we will not describe it in detail. The second model that but it's used, so I just wanted to mention it, not because this is not, I will not ask isotonic regression at the exam. Just wanted to mention it in case you find it somewhere, you know that it's a way to calibrate scores that works by mapping scores to class posterior probabilities. The one that we will analyze, because we can implement it and it leads itself to be extended for fusion without having to do anything additional with respect to what we already did in the course, is to perform calibration by building models of the score. That is, we want to obtain scores that are well calibrated. For that, scores that are well calibrated are scores that can be thresholded in a good way. What does it mean? It means that, for example, imagine class prior probability is 0.5. Imagine you have a model that gives well-calibrated scores. I will not show why these are well-calibrated, but imagine that I tell you that they are well-calibrated. The model will threshold the samples here, and then it will say that whatever is on this side is class 1, whatever is on this side is class 0 for the application 0.5, and if I change the application, I will change the threshold in an appropriate way. Now, a possible example of how this model can be badly calibrated, this recognizer one, imagine a recognizer that gives the same score distribution, so for the same, let's call this S1 of X. We have a second recognizer whose scores are the original scores minus 10. So it just takes the same scores of the first classifier, but for how it's implemented, it removes 10 from all the scores. Which means that if I look at the true class scores and at the false class score, they will have the same shape as before, but now will be located around minus 10. Which means that if I threshold with 0, you see that I'm not getting the same decisions. Especially when I threshold with 0, which says the prior probability for the two classes is the same, I will wrongly classify all points from the red class, and all the points from the blue class will be correctly classified. So I will get a DCF that is very high compared to what I would get if I were using the optimal threshold. Notice that for the well-calibrated scores, the optimal threshold is 0, means that if these are the scores for the new classifier, the optimal threshold for this prior will be minus 10. If the scores are all shifted by minus 10, to obtain the optimal threshold for the second model, I need to shift my thresholds by minus 10. So here, if I use the threshold 0, this is the theoretical one, I know that I will do very bad, because the optimal threshold is minus 10. And the decision I make with this threshold are completely different. So the idea here is, can we find a way to map back these scores here? If we are able to understand that this model was removing 10 from all the scores, we could compensate and we could build a calibrated R2 which takes the score provided by the model and adds 10. If I add 10 to the score provided by this model, I will get exactly the score provided by the first recognizer, which were, from our assumption, well calibrated. So the idea here is, can I find this kind of transformations? And the answer is yes. We can do that by creating models of the scores and analyzing how the scores behave and how they should be modified in order to recover scores that represents log likelihood ratios. Typically, the score models, depending on how we address them, will consist of either models that describe the distribution of class for the distribution of the scores of the recognizer in order to create log-like ratio models from the score themselves, or they will, as we did here, define assumptions on the transformation that we want to apply to our score, so that then we will be able to recover well-calibrated scores. For example, here I added 10. I can say that to have a calibrated score for the classifier 2, I will have to take its score and add some value beta. I need to estimate this beta. This is my calibration model. If I'm able to estimate this, then I will produce scores that are well calibrated. Or we will generalize it. We'll say that to calibrate the scores, we need to find a linear transformation of our data. Then we will define the calibration transformation as a linear function, and we will estimate its parameters. Similar to what we did when we said, okay, let's use the validation set to estimate the optimal threshold for a given application, we will need to estimate these models on a training set. And the good thing is that we will see that typically we will train our models for a specific application, which means the good fit will be obtained for that application. But although not always, typically we will see that this model performs well also for different applications. So with respect to choosing the threshold application by application, here we will have models that are trained typically for a specific application in mind, but will provide scores that will look well calibrated also for applications that are not too different, and in some cases even very different from the one we trained on. A possible way will be using exactly the logistic regression model that we have seen up to now. Now, what is the idea? The idea here is, just to summarize very quickly, the idea here is to exploit models that we know are well calibrated, well, models that typically give well calibrated scores, but that we've seen may not provide well calibrated scores when we have some specific issue, but use them in a way that this issue don't manifest. What does it mean? Let's take generative models. When we have said that generative models perform bad in terms of calibration, we have said that one possible reason why generative models perform bad is that generative model may perform bad when there is mismatch between the training and the application data, or when there is mismatch between the model assumption and the distribution of the data. For example, if my data is distributed like this for one class, then the Gaussian model will not be a good model of the data. If there is mismatch between training and evaluation set, then again, the generative model will not reflect well the evaluation set data. And we said that in these two cases, generative models will not perform well in terms of calibration. However, we know that if a generative model is good, that means it fits well the data, and to be more precise, it's a good model for the evaluation data. So if the data that I want to classify are well described by the generative model that I learned on the training set, then this will provide log-like ratios that are well calibrated. So if I have this model here for class blue, and of course the same for the other class, if this model that are trained to fit well the training set, fit well also the evaluation data, then the model will provide a good probabilistic description of the evaluation data. It will be close to the distribution of the evaluation data, so it will provide scores that are well calibrated. Now, what is the problem with generative models trained on our samples? That when we train our models on the samples are typically large dimensional. For example, you have in the project, these are 6-dimensional, in the iris, these are 4. In reality, these may be 1,000 dimensions, the dimensionality of the sample. When the dimensionality of the sample is large, having a good fit of the training set is not that easy. It's easy when samples are one-dimensional. We have seen that we can easily train a Gaussian model that fits well an histogram of samples that are one-dimensional, looks pretty much Gaussian distributed. When our samples are 1,000 dimensional, we don't even have enough training data to even understand whether the Gaussian model is a good fit, a good description of our data. We use that because it's simple to use, because it typically provides good results. But there may be models that would be much more precise for our samples. For example, in the training set, even just in the project data, you have seen that to describe features 5 and 6, Gaussian models are not a good description. Now, with real data, this is much more complex and there's much larger amount of components. Typically, our generative models may not be able to provide a good description and thus have miscalibration error. On the other hand, we know that, and of course, there will maybe mismatch between the training and evaluation population. Now, let's put this problem aside. So let's imagine there is no distribution mismatch, and there is just the issue that our generative models are not able to well describe our original samples due to the complexity of the task and the complexity of the feature themselves. However, we know that if we use generative models for simple data, for example, one-dimensional data, we can obtain scores that are well calibrated. So one possible idea here is, okay, what happens if so the original classifier gives us a log-likelihood ratio that is the density for X, the samples, given class 1, divided sample for density for sample X, given class false. Okay? And let's call this as U to remember this is non-calibrated. And this is the sample. Now, how can I transform this S into a well-calibrated value? Well, I could ask myself, what is the, if I have this S that I don't know whether, remember, when I have scores that are well and not calibrated, it means that I have this S and I don't know whether this is representing a true class or a false class sample. Miscalibration means that, for example, let's see it in a different way. Delete. Being miscalibrated means that I don't know how to threshold this, or if you prefer, I don't know whether this is favoring class 1 or class, whether I should understand this as a sample of class 1 or class 0. So what I can ask is, what is the probability that this sample belongs, that a sample that has score SU is a sample from class 1? So I can try to transform the problem into, okay, I don't know whether sample 1, sample SU represents class true or class false. Can I find a way to understand what is the probability that this samples represents class true or class false? And the answer is, imagine that I have a validation set. So now this is a validation set for which I can compute the scores given by the recognizer. So I have a validation set over which I run my recognizer. So I have score x1, samples x1 to xn. Then I compute the uncalibrated scores 1 to n for this dataset. Then I can try to look at the histogram of these scores. Looking at the histogram of these scores, I can try to understand whether a value SU equals 0.5, where is it over these histograms? Is it in the region of the red scores, or is it in the region of the blue scores? Well, if I look just at the number, I don't know. But if I have a validation set that I can use to compute the scores for many samples of the two classes, then I can try to understand where a score 0.5 would lie. So if I have my test sample for which I compute the score 0.5, by itself I wouldn't know whether this is from the true or false class, but now if I have this validation set, I can take this and compare it with the scores that I obtained for the red and the blue class. For example, imagine that the score of the red class range from -5 to +5, and the blue class go from -15 to -5, and then there may be overlap, I will address that in a moment. Then we can say that there is a much higher chance that I observe a 0.5 score if the sample came from class 1. Is it clear? I have a score that is 0.5. I need to decide to which class this sample belongs. If the model was well calibrated, then I could compare the 0.5 with a threshold. But it's not well calibrated, so I don't know whether this sample is more likely to come from the red or from the blue class. Because I don't know, because as I said, these are, let's say, the well-calibrated scores. Miscalibration moved them, so imagine they moved them. But it may have moved them in this way, so all scores are moved to the left, but it also may have moved them in this way. All the scores are moved to the right. So if I just know 0.5 and I don't know in which of these two conditions I am, I can't say anything about this 0.5. However, if I have a validation set, I can try to figure out in which of these two conditions I am. If I have a data set for which I can compute the scores of the classifier for the two classes, I can, for example, looking at the histogram, try to understand whether I'm in this situation where all the scores were moved to the left, or in the second case, where all the scores are moved to the right. I can do that by looking at the histogram. Now, looking at the histogram is not a good way to address the problem, so we can do slightly better. We can ask ourselves what? Well, I want to know from which point this sample S comes, so I can try to build a model that gives me the distribution of the scores for the true class, and a model that gives me the distribution of the scores for the false class. So rather than using histograms, I can try to fit a generative model to the scores of this validation set. So I'm fitting two distributions to these histograms. And then rather than looking at the histogram, I ask myself, what is the likelihood that I observe the score SU 0 minus plus 0.5 given class 2, and what is the chance that I see it given class false? So the likelihood computed over this, so it is 0.5, it will be somewhere here. And then I can take the ratio of these two and the logarithm. The result is a log likelihood ratio. It's a log likelihood ratio of a generative model that, in this case, does what? Well, it's well tailored for the application. We said there is no mismatch between the training and the evaluation population. But it's also a model that describes very well the distribution of the data, because it's a simple model trained over a distribution of one-dimensional samples, the scores. So what I can do is, rather than basing my decision on the score of the classifier, I create a model of the scores for the two classes, and then I use the model itself to make inference to produce a well-calibrated score. So the idea here is if I have a score that is not well calibrated, I can't use that directly because I don't know how miscalibration changed the distribution of my scores from a theoretical good distribution of the scores. So what I will do is I will create a model for the scores of the true and the false class using a data set and compute the log likelihood ratio for the uncalibrated score using the score models. So the scores themselves become training material from which I build a model, for. This will be a log likelihood ratio. Did we improve our calibration? Probably yes. We have match between the training and the evaluation population because we said we have it. And if we didn't have, then we couldn't be calibrating in any case. You would need, whenever we build a calibration model, even when we select the threshold by cross-validation, we need the validation set to be close to the evaluation set. And we will see what does it involve later. But for the moment, let's say this happens. Now, what was the other problem of the generative model? That it would not provide a good description of the features. Why? Because the model trained for the X sample, for the original samples, was not complex enough because the X samples were themselves complex, the feature vectors were complex, the feature dimensionality was large, so the generative model was not that accurate for the features. But now this model is a model trained over scores. Scores are one-dimensional. Typically, if I have a validation set, if I adjust a few hundred scores, I don't even risk overfitting because estimating a one-dimensional distribution for a few hundred samples is typically not that difficult. So if I can add, I can use even more complex model because building complex distributions for low-dimensional samples is not that hard. We didn't see it, but we can use distributions that are much more complex than just the Gaussian, that to generalize them to multidimensional would become a nightmare, but they can still be trained reasonably well on one-dimensional data. So one-dimensional, monodimensional, unidimensional distributions are easier to work with than multidimensional. The result will be a score that therefore is typically better calibrated. Now, does it respect our other request that our distribution preserves the ordering of the scores? Well, it depends on the distribution that I decide to use for the models. I will need to put constraints on the distributions. We are not going to see which ones, but by properly constraining the models for this, so by choosing models that are parametric but with some limitations on how the parameters may change, I can guarantee that. For example, I can use two Gaussian densities, but if I want to ensure that the transformation is monotonic, these two Gaussians must have the same variance. We are not going to prove it, but this is just to say that properly constrain the parameters, we can also guarantee that our distribution will preserve the order of the scores of the original classifier, and typically will produce scores that are better calibrated. So how would the whole thing work now? We have our samples, training samples, x1 through xn, from which we build our recognizer R, which produce scores that are uncalibrated. So for example, we take x1 through xn, we build R as a Gaussian model. So we have the two Gaussian that describes the two classes. Then we have a test sample, and let's draw it here because we will need to do several steps. So these are the x1 through xn. So I may have my Gaussian model that describes the samples of the two classes. How good? Well, it depends on the model and how large it is. Then, so from this data, we will estimate these two distributions. Then, at test time, what do? We compute the uncalibrated score for the test samples, logarithm of x t given mu t sigma t, and let's put an n because it's a normal, which are these two. And this is our uncalibrated score. Then we will have a validation set which samples, let's call xv1 through xv, let's call it m. For all of these, we will compute this corresponding uncalibrated score. So this is train. Then we take our validation set, we compute the uncalibrated scores, we create a model for the two classes, and let's use the two colors. This is the SU of x axis. We create a new model that consists again in two classes, in two Gaussian in this case. Let's call NC because it's a calibration of a score that is uncalibrated. So here the input is a score, and these are unidimensional. So let's call it M and V because these are one-dimensional values that are the mean and the variance of the two Gaussians. And if we said, if we want this to be monotonic, then there will be just a single V that is shared among the two, even if that makes the model a bit imprecise, but let's keep it like this because this for us doesn't really change much. So let's keep it like this, and let me remove this C because this is still a Gaussian. The fact that it's a calibration is because we passed the uncalibrated score. So from here, once we have estimated this, we compute for our test sample the calibrated score as what? The logarithm of the ratio of the uncalibrated score with the distribution that describes the uncalibrated scores for the true class and the distribution that describes the uncalibrated score for the second class. This is one possible way of producing well-calibrated scores. Of course, how good it is depends on how well I described the distribution of our scores of the original classifier. So how well this model performs depends on how well I manage to capture the distribution of the original scores. If I manage to do that well, then calibration will be good. Remember that now this model doesn't, but if we share the variance, then the model may be a bit less precise in capturing the density of the distribution, but it will preserve monotonicity. If our transformation is monotone, as long as our transformation that calibrates a score is monotone, it preserves mean DCF. So if I compute mean DCF for the new scores, I will have the same mean DCF as the original one. If I preserve the order of the scoring, also the optimal thresholding will be preserved. It will not be at the same value, but the partitioning of the scores into two sets falls lower than threshold and higher than threshold will always be the same as in the original dataset. So if our transformation is monotone, it preserves mean DCS, and typically this will result in actual DCF getting closer to minimum DCF. Of course, it relies on the distribution assumption for the score being precise, but it's reasonably easier to make models that are precise for one-dimensional densities than it is for multidimensional densities. So it's easier that this will be more precise than the distribution that I was using for the original models. Not necessarily always, but it's reasonable to expect that it will work. And of course, this can be applied to any model. It can be applied on SVMs, it can be applied on the output of a generative model. here we applied it on the output of a generative model, but this S could be the SVM model. So it could be just the SVM score. Then I would do the same thing, but now here I would create a distribution model for the SVM scores. And then I would use that model, which now is a probabilistic model, to create a probabilistic version of the SVM. So to see it, do I need to show it? So if you want to apply this to an SVM, what do you do? You would have samples x1 through xn. You would optimize your objective. This will give you W and B, and the scoring for the test, the uncalibrated score, would be W transpose X plus B. Then, with the validation set, you would take the validation data x1 through xm, compute all the scores for this. This would result in some distribution that typically, well, maybe wherever it is, I don't know where it is, maybe something like this. Now, they may also overlap. Before I was showing them non-overlapping, but typically this will overlap, otherwise our mean DCS would be 0 because it would be easy to perfectly separate the classes. Now we feed a model for the scores of these two. The calibrated score will be what? Will be a log-likelihood ratio for the uncalibrated scores, exactly like before. But this time, this will be W transpose XT plus B, so the score of the SVM. Nothing would change before, just the way I generate my uncalibrated score. Now I have a SVM and an SVM score that I can use as a log-likelihood ratio. Now, if I followed up to now, you have heard me saying that this works well when I can find a good model for these, for the scores. So the question is, it may be easy, but it may not always be that easy. We can show that even with simple model, we may have distribution that looks like weird. For example, distribution that looks like this. Makes perfectly sense. So this kind of shapes you can't really fit, or let's do it like even more. This kind of shapes you can't easily fit with a Gaussian model, because a Gaussian model here would fit like this. Because the Gaussian model is symmetric. If you have something that is asymmetric, you can't fit it with a Gaussian model. So you will need to devise another distribution model for the scores. Now let's go back to our score model. Let's do what I said before. We share the variance of the two models. So we assume that the variance of the two score distributions are the same. Which kind of calibration transformations do I get? How would it look like? Again, you should know the answer to this. It will look to somebody else. Okay, nobody else, so we will take the first answer as the correct one. Will be an affine transformation, where this will be a function of the parameters of the two Gaussians. So we have a simple transformation that depends on the parameters of the distribution. Now, we said sometimes it's not easy to find good distribution models for our samples. For example, the Gaussians may not be good enough. But in many cases, we're not going to show it, but in many cases, a linear transformation for the scores may be enough. Remember, when I mentioned the isotonic regression, we can show that the isotonic regression that we didn't discuss is optimal for, it's an optimal calibration transformation for the data is trained on. So if I look at the calibration transformation of the isotonic regression on the training set, it will be optimal. If I look at it, I will see that there are long regions in space where this can be well approximated by a linear function. This I just tell you so. So take this for granted true, and let's say, okay, now we don't have a good model of these distributions, but we know that for us, linear calibration is enough. So we want our calibration transformation to be linear, but we don't want, which is what a simple Gaussian model would give, but we don't want to explicitly model the distribution of the samples. How can we obtain a model that gives well-calibrated scores, and why would we expect this to be well-calibrated? Let's go back and think in terms of the classifier. We want a classifier that has linear decisions, but we don't want to explicitly model the distribution of features. What was that? Was logistic regression. We said we use logistic regression as an alternative where we fix the decision rule and we don't want to model explicitly the mapping, the distribution of the features, but we define a way to compute the score as a linear function. The score of the logistic regression is a linear affine function to which we gave a probabilistic interpretation. So we estimated W and B in a way that the score could be interpreted as what? The sigmoid of the score would be the class posterior probability for plus true. Then we said, okay, that's not enough for our model. Let's do a model where the score is not interpreted, so the score itself was the logarithm between class posterior. Then, what do we said? If we want a model that does not produce a score that is interpreted as a class posterior ratio, but we want the same model, but with a score that represents a log likelihood ratio, what would we do? We said that the log, say it. We said that the log likelihood ratio score contains the models, the distribution, the prior probability of the training set. So if we take this minus the empirical training set prior, this is a score that, if all goes well, will behave like a log likelihood ratio. Still, it's trained for a given application, this application, but then it would perform well also for other applications. We saw that. And what did we say we can do if we don't want the model to be tuned to the application empirical prior, but to any application that we provide in advance? What would we do if we don't know, if we don't want to use the empirical training set prior as prior, but we want the model to be tuned for application pi t? We said that we can modify the model using the prior weighted model that would essentially weight the two class contributions Here I put zi, but zi is +1, of course, in this case. And then I would have the false class that I put in front, but it's the same. The same thing with the false class points. This model would learn something that behaves, that sees samples as if the proportion of the samples was pi t. So as if the empirical training set prior was pi t. And then here we wouldn't remove the empirical anymore, but we would be removing our pi t directly. So this model can be trained for a specific application to provide scores that are tuned for that application and typically well calibrated for other applications. Why I say typically? Why did we say that the logistic regression may not provide scores that are well calibrated? We saw at least two possibilities, which are related to the same problem. What is the main problem that affects that may affect logistic regression? Overfitting. We say if we overfit, our model becomes too confident, so this will be not well calibrated anymore. So we added a regularizer. What do we say that may happen if we add a regularizer to the logistic regression? Generalize too much, but becomes less underconfident. So all the probabilities become very close to 0.5. So it generalizes well as a separation rule, but the values that it gives to the probabilities are underconfident. So the score will again not be well calibrated. When overfitting happens, what should my data have for overfitting to happen? Why do I have overfitting? When do I have overfitting typically? What is overfitting due to? What is that is causing overfitting? How is overfitting related to a model? Not just logistic regression, but to any model. Overfitting you should have seen also in previous courses. Too much complex, yes. So what does it mean too much complex in the sense of here? That it has what? It has a lot of, in this case, a lot of parameters. When does the logistic regression has a lot of parameters, if we consider just the linear one? How many parameters does the logistic regression have? When our feature vector is large, the parameters of the logistic regression are the dimensionality of the feature vector plus 1. So when the samples are large, we have more parameters. So we need more samples to find a separation, a robust separation rule. That's the same with Gaussian models. The more the higher the dimensionality of the samples, the more the parameters of the covariance matrix and of the mean. So the more samples we need to estimate reliably a covariance matrix. So again, typically, we will need to regularize when our feature vectors are reasonably, typically large. Which means that if our feature vectors are very small, up to one-dimensional, do we risk really overfitting? Typically, if we have even few hundred samples, there is a low, well, we need to have some errors in those samples, but if we have even few errors in our data set, since they are one-dimensional, there is not much that the model can do to avoid those errors. So even in the optimal scenario, it will still make some errors. Imagine that you have, for example, two-dimensional data. Here I can try as much as I want, but a couple of errors I will do. If I increase the dimensionality, I may have that all the red points are at this height and the blue points are at this height. So they overlap in this sense, but I can find a separation rule that is, in another way, gives much less errors. It's difficult to draw, so imagine that I take the blue samples and I lift them up, then I can separate with an horizontal plane. So the more dimensions I have, the easier it is to find a plane that separates them typically, separates the training set. If I cut dimensions, I'm cutting ways that I can separate my samples with fewer errors. We can imagine that if our samples are one-dimensional and we have some errors even with the optimal solution, then the model will not overfit because it will, in any case, we will not be able to find solutions that have so few errors that it becomes overconfident. So that means that if we have low-dimensional samples, then the scores that we get by using a prior weighted model trained for a specific application will be tuned for that application and typically perform well also for different applications. So how can we use this to solve our problem? Our original problem was we want to compute a calibration transformation. Now we fix to be linear. And we want this to be a well-calibrated log-large ratio. What can we do? Before we were training a generative model on the scores. Now we've showed under which condition the prior weighted will give us something that behaves like a well-calibrated log-large ratio. So what can we do? Train a prior weighted calibration model for a given application on a validation set. Of course, we are optimizing the model for a specific application. For that application, the model will have the best calibration. But if our transformation is general enough, so it approximates well enough the isotonic regression transformation for the application data, then we may have hope that that calibration will extend also to other applications. So what we would have here is we start, for example, from our SVM. Let's do SVM. So we do the SVM model. So from let's do all the steps. We have our training set. We have samples x1 through xm, xn, from which we estimate w and b. So the scoring function is w transpose x plus b, the one that gives the uncalibrated score, the SVM score. So this is what we already know how to do. Then we take our validation set. We take scores x1 v through xm v, the validation training set scores. Then, for this, we compute the uncalibrated scores, which will have some histograms, but in this case, we don't really care about the histogram because we can look at them, but we will not be using it. From this, we use these as if they were one-dimensional samples to train a prior weighted logistic regression. Prior weighted logistic regression means what? A model whose objective function is pi t, our target, divided the number of true samples. This is NTV because it's the validation set. Sum over what? The samples such that the class for the sample ith of the validation set is true. So true scores of validation set. Logistic loss, 1 plus exponential of minus what is our mapping. The calibrated score is a linear mapping of the non-calibrated score minus the prior log odds. This is the mapping that we want to estimate. Now, regarding how you want to implement, you have on the slides the explanation for both. You can just train the original logistic regression without this term. This will not give you a calibrated log likelihood ratio. This will give you a posterior log ratio score that then you can convert by removing explicitly the term. So actually here what we will train is alpha uncalibrated plus beta. I don't put the z because this is class true. But if you want, here you can put zi, which is 1 for these samples. Plus the same thing for the false class, so false scores. Log loss, 1 plus exponential of minus zi, which in this case is minus 1. So this is minus 1. Alpha score, of course, I plus B. So this SUI is the SU of Xi, of course. So here is the score for the sample Xi of the validation set. You train this model. This will give you an alpha star and a beta star that are obtained by minimizing this respect to alpha and beta. So the solution of the logistic regression objective, maximum likelihood solution or minimum log loss. Remember that this is still the maximum likelihood solution. So those under which the class label assignments are the best. And then for a test score, you will compute first the uncalibrated score. Then you will compute the posterior ratio, which is alpha star SU plus beta star. And then, as usual, the calibrated score for the sample, which is alpha star SU of XT plus beta minus the log odd that was used for training the model. Okay? So this pi t here. Now, if you want a model that directly gives you the alpha, notice that the difference is that I have a different beta value here. If you want to train a model that directly gives you the values of alpha and of this sum, you can actually train a different model where in the parentheses there you put alpha SU plus beta plus the log odd of the prior, which means that what you estimate in beta is beta minus the log prior. So then your calibrated score will be just this. But this doesn't really change much. If you train a model where the score here is already the score plus the prior log odds of the training set, then the beta prime that you will estimate is the beta prime that contains the original beta minus the log odd. Because once you train the model, you would have that the beta star will be equal to beta prime star plus the log odd. So beta prime star will be beta star minus the log odd. So you can optimize the model, but it's not really necessary. You can just train the original model and then at the end compensate for the prior log odds that you trained. This was just to say that you have on the slide, you could train a model that directly gives you this constant. So it will look like a linear function directly, the output of the model, but it doesn't really change. For what we've seen, this is sufficient. This is how you can do the whole thing. So you decide that your calibration model is linear. Notice that your final calibration is again linear because the calibration transformation now is alpha SU plus beta minus log pi t divided 1 minus pi t. If I call this beta prime, this alpha SU plus beta prime. So it's a linear function. We're just, whether this is computed directly inside beta or outside doesn't change the fact that it's still an affine function. So we have an affine transformation of our data trained by a logistic regression. Question, should I add a regularizer here to the logistic regression? Yes. Yes. So typically we will not need, because the risk of overfitting is low. We have a very simple model, just two parameters, alpha and beta. Those are scalars, so there are two values to estimate. That's because our input features are the scores of the validation set, so they are one-dimensional samples. They are vectors of just one component. The scores, you can see them as values, you can see them as vectors, which is what we'll do in the next laboratory next week, as vectors with one component. Therefore, the risk of overfitting is low if you have a reasonable amount of points. Reasonable amount of points with respect to what? To the dimensionality of the model. Since the samples are unidimensional, we just need few tens, maybe hundreds, few hundreds points are typically sufficient to obtain good models without overfitting. Of course, if the task is very, very easy, then we may need a bit more because the task is very, very easy. But if the task is very, very easy, even if we have a bit of miscalibration, our cost will still be very, very low in any case. So probably will not matter that much. But in any case, if we have very few errors, so the task is very easy, that even with few hundred samples we don't have almost errors, then we may risk overfitting a bit. But in any case, our cost will still not skyrocket, but we need to pay attention. But in typical scenarios, if we have reasonable amount of errors, then just few hundred samples will be sufficient. And remember that if the samples are very, very easy to classify from their scores, it means that a model trained over the original features also was overfitting a lot in terms of the scores that it provided. Because if the task is very easy, we know that logistic regression will overfit in terms of, it may provide still good classification rule, but the calibration of the logistic regression will still be very bad. So this model may fail when the task is extremely simple. In that case, we may need more data, or we may want to still add a bit of regularization, not much. But in most cases, we don't want to add regularization because we don't need it, and because we know that if we regularize too much, then our model will become underconfident. In this case, we don't risk underconfidence because we don't regularize, and in the typical use case, where we have enough samples compared to the dimensionality of the complexity of the model, it's one-dimensional, that we don't risk overfitting, the model will provide scores that are well calibrated and will work well regardless of the distribution of the scores, as long as what is the limit? In this case, the limitation of the goodness of the model is the complexity of the mapping function. So the model will behave well if a linear function can find a good mapping for a large variety of scores. This is not always true, but in many cases it will, in the sense that for the application that we're training on, we'll have good calibration. And if the linear assumption is good, we'll have also good calibration for applications that are not too far. What does it mean, not too far? Typically, well, it depends on the task, but in many tasks, we can see that even applications that are quite far, for example, you may, in the task that we work on, you may train for an application whose prior is 0.1, it will work well for applications whose prior is also 0.01, so one order of magnitude of difference. So typically it will perform well, not just for the target application, but for a good range. Of course, if our application is very, very far, we may need to train a different model for that application. One thing that we could do is, for example, we may train different models for different applications, and then based on the actual application, we decide which of these models is probably better for that specific task. But at least we don't need to retrain everything from scratch every time. And if we have a good reason to choose reasonable values for the applications, we may obtain good results even if we don't get exactly the target application. Generative models, on the other hand, don't have this issue. If the assumptions on the distribution are good, they will generalize to a huge range of applications. The larger the range of application, essentially depends on how well I fit my samples. But of course, having a good fit for the distribution of scores may require models that are much more complex than just a simple Gaussian model. So we pay it that we can have better calibration with generative models, but this requires to have much more deeper knowledge on how to model the distribution of the scores themselves. And then we would be less application dependent. With a logistic regression model, we have a more simple approach, which is a bit application dependent. I say a bit because choosing the right application for training is much less critical than choosing the optimal threshold for a given application on a validation set. Typically, the linear transformation will perform reasonably well for also other applications.